Picture the skies over Europe in 1945. Propeller-driven armadas blackening the sun, raining high explosives down on the Axis war machine in a slow, brutal war of attrition. Now, fast forward just 5 short years, those same skies are ripped apart by something entirely different. A silver dart with wings swept back like a predator diving for the kill, leaving 6 screaming trails of jet exhaust in its wake. This is the story of the Boeing B-47 Stratojet. It is the most important bomber you have probably never heard of. While the B-52 Stratofortress gets all the Hollywood glory, and the B-29 Superfortress gets the historical credit for ending the Second World War, the B-47 was the actual loaded gun pointed directly at the head of the Soviet Union during the most dangerous, unstable years of the early Cold War. Before we dive into the titanium, the jet fuel, and the terrifying nuclear calculus of the 1950s, let me ask you a question. If you had to bet the absolute survival of the United States on a single piece of radically untested technology, would you risk it all on a design that even its own test pilots initially thought was a high-speed death trap? Let me know your thoughts in the comments below. Welcome back to the channel, where we dissect the machines, the tactics, and the brutal realities of military history. If you want to understand how the modern battlefield was actually forged, hit that subscribe button, ring the bell, and join the ranks. We do not do surface-level summaries or Wikipedia reads here. We dig into the blueprints, the logistics, the doctrines, and the raw firepower that shaped our world. To understand why the B-47 Stratojet had to exist, you have to understand the sheer, unadulterated panic that gripped the Pentagon in the years immediately following the Second World War. On August 14, 1945, the United States possessed the most devastating military machine in human history. By 1947, that machine had been largely dismantled. The Great Demobilization saw the United States Army shrink from over 8 million men to barely 1 million. Thousands of combat aircraft were flown to the desert and chopped up for scrap aluminum. The mighty fleets of the United States Navy were mothballed. The American public was tired of war, tired of rationing, and demanded their boys come home. But halfway across the world, Joseph Stalin did not demobilize. The Soviet Union kept its massive, mechanized armies parked right in the heart of Europe. We are talking about the group of Soviet forces in Germany, an absolute juggernaut of conventional military power. This was not a defensive garrison. This was an offensive spearhead consisting of elite units like the 1st Guards Tank Army and the 3rd Shock Army. They had thousands of T-34-85 medium tanks and the terrifying new IS-3 heavy tanks, which had shocked Western observers at the 1945 Berlin Victory Parade. The Allied commanders looked at the IS-3 with its thick, sloped armor and massive 122mm gun and realized that our M4 Shermans and M26 Pershings were hopelessly outclassed. If the balloon went up and World War III kicked off in Europe, the Red Army was projected to reach the Rhine River in 7 days and the English Channel in 14. How do you stop 3 million battle-hardened Soviet troops from rolling across the Fulda Gap when your own army has been gutted by budget cuts? You do not stop them with artillery, and you do not stop them with tanks. You stop them with the threat of absolute, instantaneous nuclear annihilation. This was the birth of the doctrine of massive retaliation. The United States would offset Soviet conventional supremacy on the ground with American atomic supremacy in the air. But there was a massive glaring problem with this strategy. Having the atomic bomb is useless if you cannot deliver it to the target. In the late 1940s, the American nuclear arsenal consisted of weapons like the Mark III and the newly developed Mark IV atomic bombs. These were not the compact, sleek warheads we have today. They were massive, delicate, 10,000-pound physics experiments that required a massive bomber to carry them. At the time, the primary delivery vehicle was the Boeing B-47 Superfortress, the same piston-engine bomber that had leveled Japan. But the B-29 had a top speed of around 350 miles per hour. Against the propeller-driven fighters of World War II, that was adequate. But the world had changed. The jet age had arrived. The Soviets were rapidly developing jet fighters, culminating in the Mikoyan-Gurevich MiG-15. The MiG-15 could fly at nearly 670 miles per hour and was armed with devastating 23mm and 37mm autocannons. Sending a formation of slow, propeller-driven B-29s into Soviet airspace defended by MiG-15s would not be a bombing mission. It would be a massacre. The Air Force knew this, and their initial stopgap solution was the Convair B-36 Peacemaker. The B-36 was a Leviathan, a massive magnesium overcast powered by 6 massive radial piston engines, and later augmented by 4 jet engines. The joke among the crews was 6 turning and 4 burning. It could carry a staggering payload over intercontinental distances, but it was still fundamentally a creature of the past. Its top speed was barely 400 miles per hour. It was a massive target on radar, and it was mechanically a nightmare. The United States needed a true, pure jet bomber. They needed something that could fly at 40,000 feet, cruise at 600 miles per hour, and outrun enemy interceptors entirely. They needed a revolution. To find a historical comparison for the leap in technology required, you have to look back to 1906, when the British Royal Navy launched the HMS Dreadnought. The Dreadnought, with its all-big gun armament and steam turbine propulsion, instantly rendered every other battleship on Earth completely obsolete. It reset the global naval arms race to 0. Or consider the shift from muzzle-loading muskets to repeating rifles in the American Civil War, a technological leap that fundamentally altered the geometry of the battlefield and the lethality of the individual soldier. The United States Air Force needed its own dreadnought moment. They found it in the shattered ruins of Nazi Germany. In May 1945, a team of American scientists and engineers, part of Operation Lusty, was scouring defeated Germany for aeronautical research. Among them was George Scherer, a brilliant aerodynamicist from the Boeing Company. While sifting through the secret Hermann Göring Aeronautical Research Institute in Braunschweig, Scherer came across a treasure trove of wind tunnel data that would change the course of aviation history. The data centered on a concept proposed by a German aerodynamicist named Adolf Bussmann back in 1935. Bussmann had theorized that sweeping an aircraft's wings backward would delay the onset of compressibility drag, the invisible aerodynamic wall that aircraft hit as they approached the speed of sound. In 1935, nobody cared, because planes were barely doing 200 miles per hour. But in 1945, with the advent of the jet engine, Bussmann's theory was the holy grail. The Germans had already applied it to the Messerschmitt Me-262 fighter, but they had vast amounts of data on how to apply it to larger, heavier aircraft. Scherer immediately realized the implications. At the time, Boeing was working on a jet bomber concept for the Air Force called the Model 432, which featured straight wings and jet engines buried in the fuselage. It looked like a slightly sleeker jet-powered B-29. Scherer sent an urgent message back to Seattle: "Stop the straight-wing design immediately." This single piece of captured intelligence sparked the genesis of the B-47. Boeing completely scrapped their conventional blueprints and went back to the drawing board. They designed a radically new aircraft, the Model 450, which would become the B-47. The design was so futuristic it looked like something out of a science fiction magazine. The most prominent feature was the wings. They were swept back at a severe angle of 35 degrees. This was unprecedented for a heavy bomber. The swept wing allowed the B-47 to slice through the air at high subsonic speeds, delaying the shock waves that caused drag and buffeting. But a swept wing of that size created massive structural challenges. It had to be incredibly thin to maintain aerodynamic efficiency, but it also had to be strong enough to lift a 200,000-pound aircraft off the runway. Boeing engineers had to pioneer new manufacturing techniques, moving away from the thin sheet metal of the World War II era to thick, heavily milled aluminium alloy skins. The wings were so flexible that on the ground they drooped downward, but in flight they would flex upward by as much as 5 feet at the tips. This flexibility was intentional, designed to absorb the brutal aerodynamic stresses of high-speed, high-altitude flight. But where do you put the engines on a wing so thin? You cannot bury them inside the wing root, which was the approach the British took with their V bomber force, like the Avro Vulcan and the Handley Page Victor. Burying the engines in the wing increases aerodynamic efficiency, but it also makes maintenance a nightmare and creates a catastrophic risk if an engine catches fire. And in the late 1940s, jet engines caught fire a lot. Boeing's solution was brilliant, and it became the standard for almost every commercial airliner built since. They hung the engines on pylons underneath and forward of the wing. These were called podded engines. Why put the engines on pylons, where they create parasitic drag? Because when a primitive turbojet decides to violently disassemble itself or burst into flames, you want that explosion to happen outside the airframe, not inside the wing structure where the main fuel tanks are located. Furthermore, the podded design acted as a mass balance. By placing the heavy engines forward of the wing's center of gravity, it helped dampen flutter, a deadly aerodynamic vibration that could literally tear a swept wing off an aircraft in mid-air. The B-47 was equipped with 6 General Electric J-47 turbojet engines. 4 were paired in double pods near the inboard section of the wings, and 2 were mounted in single pods near the wingtips. The J-47 engine was a marvel of its time, but by modern standards, it was an incredibly primitive and underpowered piece of machinery. Early versions produced just over 5,200 pounds of thrust each. Even with 6 of them, the B-47 was severely underpowered on takeoff, especially when fully loaded with 10,000 pounds of nuclear weapons and tens of thousands of gallons of jet fuel. To get this beast off the ground, the engineers had to resort to brute force solutions. They incorporated a water alcohol injection system. During takeoff, a mixture of water and methanol was pumped directly into the engine compressors. The water cooled the air, increasing its density, which allowed more fuel to be burned, temporarily boosting the thrust to around 7,200 pounds per engine. It produced a deafening roar and a massive trail of black smoke, but it got the plane into the air. If that was not enough, the B-47 was designed to use JATO, or jet-assisted takeoff rockets. An array of up to 33 solid-fuel rocket bottles could be mounted on the aft fuselage. When ignited, they provided a massive, terrifying burst of auxiliary thrust, turning the bomber into a temporary spacecraft to hurl it off a short runway. The radical wing and engine placement led to another bizarre design choice. Because the engines were under the wings and the wings were shoulder-mounted high on the fuselage, there was no place to put conventional tricycle landing gear. Furthermore, the belly of the aircraft was entirely consumed by the massive bomb bay and the enormous fuel tanks required to feed 6 thirsty jet engines. The solution was the bicycle landing gear. The main landing gear consisted of 2 massive twin-wheel struts mounted directly on the centerline of the fuselage, one forward of the bomb bay and one aft. To keep the aircraft from tipping over on its wings, 2 small outrigger wheels were mounted on the inboard engine pods. This configuration solved the packaging problem, but it created an absolute nightmare for the pilots. You could not rotate a B-47 on takeoff like a normal aircraft. If you pulled back on the yoke to raise the nose, the rear landing gear would act as a pivot and you would strike the tail on the runway. The aircraft had to be flown off the runway almost perfectly level, relying entirely on the lift generated by the wings as speed increased. Landing was even worse. You had to touch down on both the front and rear main gear simultaneously. If you landed on the front gear first, the aircraft would bounce violently, a phenomenon known as porpoising, which could easily destroy the airframe. While Boeing was wrestling with the physics of the B-47, the geopolitical situation was deteriorating faster than anyone in Washington had anticipated. In 1948, the Soviet Union blockaded West Berlin, cutting off all road and rail access. The United States and its allies responded with the Berlin Airlift, a monumental logistical effort to keep the city alive from the air. But the blockade was a stark wake-up call. War with the Soviet Union was not just a theoretical possibility, it was a looming probability. Then, in August 1949, American reconnaissance aircraft detected radioactive fallout over the Pacific. The Soviet Union had detonated its first atomic bomb, Joe 1, years ahead of CIA estimates. The American nuclear monopoly was gone. The stakes had just been raised to absolute annihilation. The following year, in June 1950, North Korean forces, backed by Soviet and Chinese hardware, flooded across the 38th parallel. The Cold War had turned hot. In the skies over Korea, the shock of the MiG-15 became a brutal reality. American B-29s, taking off from Japan and Okinawa, were mauled by the swept-wing Soviet fighters. The United States Air Force had to suspend daylight bombing raids because the losses were simply unsustainable. The message was clear. The propeller-driven bomber was dead. The B-47 was no longer just an experimental project, it was a matter of national survival. To wield this new weapon, the United States turned to the Strategic Air Command, or SAC. In 1948, SAC was taken over by General Curtis LeMay, a cigar-chomping, ruthless tactician who had orchestrated the firebombing campaign against Japan in World War II. When LeMay took command, he found an organization in shambles. He ordered a mock bombing raid on Dayton, Ohio, to test the readiness of his forces. The results were pathetic. Not a single bomber successfully completed the mission as briefed. Crews were untrained, aircraft were broken down, and the command structure was lethargic. LeMay realized that a strategic deterrent is only effective if the enemy believes you can actually execute the mission. He completely rebuilt SAC from the ground up, turning it into the most disciplined, heavily funded, and terrifying military organization on the planet. LeMay's philosophy was simple. We are at war right now. The shooting just has not started yet. He demanded constant training, relentless readiness inspections, and a culture of absolute perfection. Under LeMay, SAC became a machine designed for one singular purpose, delivering nuclear weapons to the Soviet Union within hours of receiving the presidential order. But integrating the B-47 into LeMay's SAC was a monumental challenge. It was not just a new airplane, it was an entirely new way of fighting. The transition from the B-29 to the B-47 was like asking a truck driver to suddenly pilot a Formula One race car. The B-47 required a crew of only 3 men, a pilot, a co-pilot, and a navigator bombardier. This was a massive reduction from the 10 or 11 men required to fly a B-29. The pilot and co-pilot sat in a tandem fighter-style canopy, completely isolated from the navigator, who sat down in the nose. The physical and mental workload on these three men was staggering. They were flying an aircraft that demanded constant attention, operating complex early-generation analog computers and radar bombing systems, all while wearing bulky pressure suits in a cramped, freezing cockpit. The industrial effort required to build this fleet was equally staggering. Boeing's plant in Wichita, Kansas, became the epicenter of B-47 production. They had to invent new tooling, new riveting techniques, and new quality control standards. Eventually, Douglas and Lockheed were brought in to build the B-47 under license, just to meet the Air Force's insatiable demand. At the height of production, they were rolling a new B-47 off the assembly line every single working day. Over 2,000 B-47s would eventually be built, making it the most produced jet bomber in history. Consider the logistical tale required to keep this massive fleet operational. Jet engines guzzle fuel at an astonishing rate. The B-47 had a combat radius of around 2,000 miles. That is impressive, but it is not enough to take off from the continental United States, fly over the North Pole, drop a nuclear weapon on Moscow, and fly back. To make the B-47 a true intercontinental threat, the Air Force had to master the art of mid-air refueling. They developed the KC-97 Stratofreighter, a massive propeller-driven tanker equipped with a rigid flying boom. But here was the fatal flaw in that early system. The KC-97 was slow. It was a piston-engine aircraft. The B-47 was a high-speed jet. To refuel, the B-47 pilot had to slow down to his near-stall speed, while the KC-97 pilot had to push his engines to the absolute red line, diving slightly to maintain enough speed for the jet to stay airborne behind him. It was a terrifying, high-stakes ballet, performed at 20,000 feet, often in terrible weather, with millions of pounds of highly flammable aviation fuel flowing between the two aircraft. The logistics of the B-47 fleet rivaled the complexity of the Red Ball Express in World War II or the massive island-hopping supply chains of the Pacific Theater. It required forward operating bases in the United Kingdom, Spain, and Morocco. It required massive underground fuel storage facilities, thousands of mechanics, and a supply chain of spare parts that stretched across the globe. The B-47 Stratojet was an engineering marvel, an industrial triumph, and a strategic necessity. It gave Curtis LeMay the hammer he needed to hold the Soviet Union at risk. It proved that swept wings, podded engines, and high-altitude jet flight were the future of military aviation. But having the ultimate weapon on the tarmac is only half the battle. The true test of a weapon system is not its top speed on a spec sheet or its theoretical payload. The true test is what happens when you take this fragile, temperamental, radically new machine and thrust it into the unforgiving, brutally cold reality of frontline operations. We have built the bomber, and we have trained the men. But how exactly do you take a jet designed to fly high and fast and adapt it to survive against a Soviet air defense network that is evolving faster than anyone thought possible? The initial answer to surviving the Soviet air defense network was rooted in the absolute limits of 1950s aerodynamics. The doctrine was simple in theory, but terrifying in practice, dictating that the B-47 Stratojet would fly higher and faster than any interceptor or anti-aircraft artillery could possibly reach. To execute this, the crews had to operate in a hostile environment at 40,000 feet, where the outside temperature plummeted to minus 65 degrees Fahrenheit, and the air was so thin that sudden depressurization meant unconsciousness in less than 15 seconds. But flying a swept-wing jet bomber at maximum weight and maximum altitude introduced these pilots to a deadly aerodynamic phenomenon known as coffin corner. To understand coffin corner, you have to understand the razor-thin margins of high-altitude jet flight. As the B-47 climbed into the thinner air, its stall speed, the minimum speed required to keep the wings generating lift, steadily increased. Simultaneously, the speed of sound decreased due to the freezing temperatures. If the B-47 flew too slow, the thin air would fail to support the aircraft, resulting in a catastrophic high-altitude stall from which recovery was nearly impossible. If it flew too fast, the airflow over the thickest part of the swept wing would reach supersonic speeds, creating localized shock waves that would disrupt the lift, violently pitch the nose down, and rip the wings off the fuselage, a condition known as Mach buffet. At maximum gross weight over Soviet airspace, the margin between stalling and Mach buffet could shrink to as little as 5 knots of indicated airspeed. Could you hold a control yoke perfectly still for 10 grueling hours, knowing that a sudden gust of wind or a momentary lapse in concentration would send you tumbling into a death spiral? The pilots of the Strategic Air Command did exactly that, day after day, navigating an invisible tightrope in the stratosphere. Navigating and bombing from that altitude required a technological leap that matched the aircraft itself. The B-47 was equipped with the K system, a massive, incredibly complex bombing and navigation radar system that weighed over a ton and contained more than 1,000 fragile vacuum tubes. This was not the GPS-guided push-button warfare of today. The K system was an analog electromechanical computer. The navigator bombardier, sitting in isolation down in the plexiglass nose of the aircraft, had to constantly feed the computer variables like wind speed, barometric pressure, altitude, and ballistics of the specific nuclear weapon in the bomb bay. He would peer into a radar scope that displayed a crude, glowing green map of the terrain below, trying to identify specific radar offset aiming points, perhaps a river bend or a rail yard that would guide the crosshairs to a target hidden by solid cloud cover. The primary payload for this apocalyptic mission was the Mark 15 nuclear bomb, a weapon that weighed 7,600 pounds and yielded an explosive force of nearly 4 megatons. That is roughly 250 times the destructive power of the bomb dropped on Hiroshima. Because of the severe safety protocols of the early Cold War, these weapons were not fully assembled on the ground. They required in-flight insertion. As the bomber approached enemy airspace, the navigator had to unbuckle from his ejection seat, crawl through a narrow, freezing, unpressurized tunnel into the bomb bay, and physically insert the nuclear core into the high-explosive lens assembly of the bomb using specialized hand tools. It was a claustrophobic, nerve-wracking procedure performed while the aircraft was vibrating violently at near Mach 1. To defend itself during this penetration, the B-47 was fitted with the A-5 fire control system, a radar-guided tail turret armed with twin 20mm autocannons. There were no waist gunners or top turret operators like in the bombers of World War II. The co-pilot, sitting in the rear seat of the tandem canopy, could manually aim the guns, but the system was designed to automatically acquire, track, and fire upon enemy fighters approaching from the rear hemisphere. In reality, the A-5 system was notoriously unreliable, prone to radar clutter and mechanical jamming in the extreme cold. But more importantly, the defensive paradigm was shifting. Just as the B-17 Flying Fortress crews of the 8th Air Force learned during the bloodbath over Schweinfurt in 1943 that heavily armed bombers could not survive unescorted daylight raids, the B-47 crews were about to learn that altitude was no longer a sanctuary. By the mid-1950s, Soviet intelligence and engineering had caught up. The Mikoyan Gurevich Design Bureau rolled out the MiG-17 and then the supersonic MiG-19, interceptors that could easily reach the B-47 in the stratosphere. But the true death knell for the high-altitude doctrine was the introduction of the S-75 Dvina, known to NATO as the SA-2 guideline. This was a radar-guided surface-to-air missile, essentially a flying telephone pole, packed with a 430-pound fragmentation warhead capable of reaching 60,000 feet at Mach 3. The Soviets deployed these missile batteries in massive concentric rings around Moscow, Leningrad, and critical military-industrial complexes in the Ural Mountains. Flying a B-47 straight and level at 40,000 feet into an SA-2 engagement zone was no longer a bombing run. It was a highly organized suicide pact. Faced with the total obsolescence of their primary strike tactic, the Strategic Air Command had to completely rewrite the operational playbook for the B-47. If they could not go over the Soviet radars, they would have to go under them. This birthed the era of low-level penetration. The concept was to drop the massive bomber down to just 500 feet above the ground, flying at roughly 450 knots, using the curvature of the Earth and the terrain itself to mask the aircraft from Soviet early warning radars. But dropping a free-fall nuclear weapon from 500 feet presents a fatal physics problem. If you open the bomb bay doors and drop a 4-megaton weapon while flying straight and level at low altitude, the blast wave and thermal flash will instantly vaporize your own aircraft before you can fly out of the destruction radius. The solution was one of the most violent and terrifying flight maneuvers ever conceived for a heavy bomber. The Low Altitude Bombing System, or LABS, commonly known as toss bombing. Here is how this maneuver was executed in reality. The B-47 would approach the target at treetop level, flying at maximum military power. At a precisely calculated initial point, the pilot would pull back hard on the yoke, subjecting the massive bomber and its crew to a bone-crushing 2.5 G-force pull-up. The aircraft would pitch up into a vertical climb, essentially initiating a half-loop. As the nose passed through 45 degrees of pitch, the K-system computer would automatically release the nuclear bomb. The bomb's momentum would hurl it upward and forward in a massive ballistic arc, giving it the necessary altitude to detonate effectively, while simultaneously buying the bomber crew precious seconds of time. After the release, the pilot would continue the loop, rolling the aircraft inverted at the top of the arc, and then executing a half-roll to level out, flying away from the target area in the exact opposite direction at maximum speed. It was a brilliantly engineered tactical solution, but it demanded a physical toll that the B-47 was never designed to pay. The Stratojet was built to be a high-altitude thoroughbred, with thin, flexible wings designed to slice through the smooth, thin air of the stratosphere. Down on the deck, at 500 feet, the air is thick, turbulent, and punishing. The constant buffeting from thermals and terrain-induced turbulence caused the B-47's massive swept wings to flex violently, far beyond their intended design parameters. Have you ever bent a paperclip back and forth until the metal simply snaps from fatigue? That is exactly what was happening to the aluminum wing roots of the American nuclear deterrent. By the late 1950s, routine maintenance inspections began revealing microscopic stress fractures in the lower wing skins and the massive forged aluminum attach fittings that held the wings to the fuselage. The situation became a full-blown crisis when several B-47s disintegrated in mid-air during low-level training flights, the wings literally clapping together above the fuselage before tearing away. The Air Force had to ground significant portions of the fleet and initiate Project Milk Bottle. This was a massive, desperate industrial retrofit program where thousands of B-47s were cycled through depots to have massive steel reinforcing plates bolted and riveted onto their wing roots. It added weight and reduced performance, but it kept the fleet from falling out of the sky. The B-47 had successfully adapted to the low-level mission, but it was beating the airframes and the crews to death in the process. To maintain the psychological pressure on the Soviet Union, General Curtis LeMay implemented Operation Reflex Action. The B-47 did not have the unrefueled range to strike the Soviet Union from bases in the continental United States without relying on a precarious chain of aerial refueling tankers. To shorten the response time and guarantee destruction, SAC forward-deployed massive wings of B-47s to bases encircling the communist bloc. We are talking about massive concrete footprints carved out of the earth at RAF Fairford in the United Kingdom, Zaragoza Air Base in Spain, and Sidi Slimane in French Morocco. Entire bomber wings, consisting of 45 aircraft, hundreds of aircrew, and thousands of maintenance personnel, would deploy on temporary duty rotations for 90 days at a time. The conditions at these forward operating bases were grueling. The crews lived in heavily guarded compounds known as alert shacks, located right next to the parking aprons where the bombers sat fully fueled, with nuclear weapons loaded in the bays. The crews were on a 24-hour alert status. They slept in their flight suits, boots laced, sidearms loaded. When the klaxon horn sounded, they had exactly 15 minutes to sprint to the aircraft, strap in, start all 6 jet engines, taxi to the runway, and launch. This was not a drill schedule. This was a lifestyle of perpetual, grinding anxiety. The psychological toll of knowing that every time that horn blasted, it could be the end of human civilization, broke many men. They were the tip of the spear, sitting at the absolute end of the logistical supply chain, waiting for a coded radio transmission that would order them to fly one-way missions into the teeth of the Soviet Empire. But the B-47 was not just waiting for World War III, it was actively probing the edges of it. While the bomber variants sat on alert, the specialized reconnaissance variants, the RB-47s, were flying some of the most dangerous and highly classified missions of the entire Cold War. In the spring of 1956, the United States executed Project Home Run, a massive, coordinated intelligence-gathering operation designed to map the Soviet air defense network and photograph new bomber bases in the Arctic. Operating out of Thule Air Base, a desolate, freezing outpost carved into the ice of Greenland, a fleet of over 150 RB-47Es began launching daily sorties. These were not border patrols. These were deliberate, deep penetrations into sovereign Soviet airspace over the Kola Peninsula and the Siberian coastline. Imagine the tension inside the cramped cockpit of an RB-47 as it crosses the Soviet coastline at 40,000 feet. The electronic warfare officer, known as the Raven, is sitting in a windowless compartment in the bomb bay, surrounded by primitive radar warning receivers. His screens light up with the harsh strobing signals of Soviet early warning radars locking onto their aircraft. Minutes later, the pilot spots the contrails of Soviet MiG-15 and MiG-17 interceptors climbing desperately from bases below. The RB-47s were unarmed, relying entirely on their speed and highly classified electronic jamming equipment to survive. The Ravens would blast the Soviet radar frequencies with broadband noise, trying to break the lock of the interceptors' gun sights. During Project Home Run, American aircraft routinely penetrated hundreds of miles inland, photographing airfields and submarine pens, while Soviet fighters swarmed around them, often coming within a few hundred yards, guns armed, waiting for the political authorization to fire. It was a high-stakes game of aerial chicken, a daily brush with thermal nuclear war. The Soviets were furious, filing diplomatic protests and frantically upgrading their interceptor fleets to catch the elusive Stratojets. The B-47 had proven its tactical worth, operating in the most extreme environments on Earth, from the blistering heat of Moroccan runways to the lethal cold of the Arctic Circle. It had forced the Soviet Union to expend billions of rubles on an air defense network just to counter it. It had bridged the gap between the propeller age and the era of the intercontinental ballistic missile. But the sheer operational tempo, the brutal physical demands of the low-level mission, and the relentless grinding pressure of the nuclear alert posture were pushing the fleet and its crews to the absolute breaking point. Metal fatigue was a constant enemy, and the unforgiving nature of early jet aviation meant that any mechanical failure, any slight miscalculation in the cockpit, resulted in immediate catastrophe. As the 1950s drew to a close, the Strategic Air Command was operating on a knife's edge, and it was only a matter of time before the inherent dangers of this massive, globe-spanning nuclear enterprise resulted in an incident that could accidentally ignite the very war the B-47 was built to prevent. That inevitable spark of disaster ignited in the freezing dark skies off the coast of Georgia on February 5, 1958. A B-47 Stratojet, loaded with a 7,600-pound Mark 15 nuclear weapon, was flying a simulated combat mission at 38,000 feet, acting as the enemy for interceptor squadrons scrambling from the eastern seaboard. Through a catastrophic failure of ground-controlled radar vectoring, an F-86 Sabre fighter jet slammed directly into the right wing of the massive bomber. The fighter pilot ejected, but the B-47, piloted by Major Howard Richardson, was severely crippled, its right wing heavily damaged, and an outboard engine torn partially from its mount. Richardson wrestled with the dying aircraft, attempting to bring it down to Hunter Air Force Base in Savannah, but the landing weight was too high, and the risk of the conventional high explosives inside the nuclear bomb detonating upon a crash landing was absolute. He was ordered to jettison the weapon. Over the shallow waters of the Wassaw Sound near Tybee Island, the bomb bay doors snapped open, and the weapon was dropped into the Atlantic Ocean. Richardson miraculously managed to land the shattered B-47, but the Tybee Island bomb was never recovered, resting in the silt to this day as a chilling monument to the razor-thin margins of Cold War deterrence. Did the Pentagon truly believe they could operate a global fleet of 2,000 nuclear-armed jets, flown by exhausted men on a hair-trigger alert, without eventually dropping one on their own soil? The brutal truth is that they knew the risks, calculated the acceptable losses, and decided that the accidental destruction of an American city was a statistically acceptable alternative to a deliberate Soviet first strike. Just 1 month later, on March 11, 1958, the mathematics of that grim calculation failed again, during the Mars Bluff incident in South Carolina. A B-47 heading for an overseas deployment in the United Kingdom experienced a fault in the bomb bay harness. When the navigator went back to manually engage the locking pin, he accidentally triggered the emergency release mechanism. A Mark VI nuclear bomb fell through the closed bomb bay doors, plummeting 15,000 feet into a residential neighborhood. The conventional high-explosive trigger detonated on impact, obliterating a civilian home, leaving a crater 70 feet wide, and miraculously only causing civilian injuries rather than fatalities, solely because the fissile nuclear core had been stored in a separate compartment on the aircraft. These Broken Arrow incidents forced a massive strategic reckoning within the halls of the Pentagon. The tactical doctrine of keeping heavily loaded bombers airborne at all times, known as airborne alert, was grinding the B-47 fleet into aluminum dust and exposing the American homeland to unacceptable risk. The military had to pivot, and the lessons learned from the structural and operational failures of the B-47 directly dictated the future of American strategic power. To understand the strategic legacy of the B-47, we have to look past the aircraft itself and examine the massive logistical and economic shadow it cast across the globe. The Stratojet was not just a bomber, it was an economic weapon of mass destruction, aimed directly at the Soviet treasury. We can draw a direct historical parallel to the Union Navy's Anaconda Plan during the American Civil War. The Union did not defeat the Confederacy solely through massive, decisive fleet engagements. They won by throwing an unbreakable naval blockade around the southern ports, forcing the Confederacy to expend its limited resources internally, slowly strangling its economy and its logistical capacity to wage war. The B-47 executed a nuclear Anaconda plan. By deploying hundreds of these high-speed bombers to bases in England, Spain, Morocco, and Guam, the United States forced the Soviet Union to militarize its entire massive perimeter. The Soviets could not afford to build a strategic bomber fleet to match the Americans because they were forced to pour billions of rubles into defensive measures. They had to build thousands of S-75 Dvina surface-to-air missile sites, design and manufacture tens of thousands of MiG interceptors, and construct an incredibly complex, continent-spanning early warning radar network. The B-47 forced the Soviet military-industrial complex to play defense, draining resources away from offensive weapons and agricultural development, planting the early seeds of the economic stagnation that would eventually collapse the Soviet Empire decades later. But this economic warfare cut both ways, and the sheer financial burden of keeping the B-47 operational was staggering. The J-47 turbojet engines, while revolutionary in 1947, were maintenance nightmares by the late 1950s. They required complete overhauls after just a few hundred hours of flight time, and the water injection systems used for takeoff routinely corroded the internal turbine blades. The logistical tail required to supply specialized jet fuel, liquid oxygen, and massive quantities of spare parts to forward operating bases in the North African desert or the freezing tundra of Alaska stretched the newly formed Military Air Transport Service to its absolute limits. The United States was learning a very painful lesson about the modern military-industrial complex, a lesson President Dwight D. Eisenhower would famously warn the nation about in his farewell address. The cost of maintaining a massive, standing, technologically advanced military during peacetime was a historical anomaly for the United States, fundamentally altering the national economy and intertwining defense contractors with federal policy in ways that remain deeply entrenched today. The B-47 was the first true artifact of this new era, a machine so complex and so expensive that it required a permanent war economy to sustain it. In the shadows of this economic war, the intelligence war was being fought with actual blood. While the bomber variants of the B-47 sat on the tarmac waiting for Armageddon, the RB-47 reconnaissance crews were actively fighting and dying in the unacknowledged skirmishes of the Cold War. The most infamous of these engagements occurred on July 1, 1960, just 2 months after Francis Gary Powers was shot down in his U-2 spy plane. An RB-47H, packed with highly classified electronic intelligence gathering equipment, was flying a mission over the international waters of the Barents Sea, probing the Soviet radar networks near the Kola Peninsula. A Soviet MiG-19 interceptor, piloted by Captain Vasily Polyakov, intercepted the Stratojet and, under direct orders from Moscow, opened fire with its 30mm cannons. The RB-47 was shredded, spinning out of control into the freezing Arctic waters. The pilot, Captain Bill Palm, was killed, but the co-pilot, Freeman Olmsted, and the navigator, John McCone, managed to eject. They were plucked from the freezing ocean by a Soviet trawler, dragged to Moscow, and locked in the infamous Lubyanka prison, subjected to months of brutal psychological interrogation by the KGB. They were held as political pawns until after the inauguration of President John F. Kennedy in 1961. This incident proved that the skies were no longer safe, even in international airspace, and that the era of the manned subsonic reconnaissance bomber probing Soviet borders was rapidly coming to a violent end. The rapid obsolescence of the B-47 is perhaps its most fascinating strategic characteristic. How do you justify bankrupting your own treasury to build over 2,000 bombers that will be obsolete before the paint dries? We can compare the B-47's lifespan to the massive coastal defense networks built by the United States at the end of the 19th century. Known as the Endicott board forts. The US government spent millions constructing massive concrete bunkers armed with disappearing guns along the coastlines to defend against battleships, only to have the entire concept rendered completely useless within a decade by the invention of the airplane and the aircraft carrier. Similarly, the B-47 was a technological marvel in 1950, but by 1960, it was a flying dinosaur. The introduction of the intercontinental ballistic missile, specifically the solid-fueled LGM-30 Minuteman, changed the geometry of nuclear war forever. An ICBM could deliver a nuclear warhead to Moscow in 30 minutes, traveling at Mach 23, completely immune to interception by any technology existing at the time. Furthermore, Boeing had taken every brutal lesson learned from the B-47. The flexible wings, the podded engines, the terrifying takeoff characteristics, and used them to design the ultimate heavy bomber, the B-52 Stratofortress. The B-52 had the range to strike the Soviet Union from bases in North Dakota without relying on a fragile chain of aerial refueling tankers. And it had the payload capacity to carry massive standoff weapons like the Hound Dog cruise missile, allowing it to launch its weapons from hundreds of miles outside the lethal radius of Soviet surface-to-air missiles. By 1965, just 18 years after its first flight, the massive fleet of B-47 Stratojets was systematically flown to the Aerospace Maintenance and Regeneration Center at Davis-Monthan Air Force Base in the Arizona desert. The great silver armadas that had held the line during the most terrifying days of the nuclear standoff were unceremoniously chopped into scrap metal by massive guillotines to comply with international arms reduction treaties. The B-47 never dropped a bomb in anger. It never engaged in the apocalyptic combat it was designed for. But to view that as a failure is to fundamentally misunderstand the nature of deterrence. The weapon you build to fight a war is a tactical tool. but the weapon you build that is so terrifying, so capable, and so constantly present that the enemy refuses to pull the trigger. That is a strategic triumph. The men who flew the B-47 lived in a state of perpetual grinding exhaustion, battling horrific weather, primitive technology, and the constant suffocating dread of initiating the end of the world. They forged the tactics, the logistics, and the ruthless discipline that still define the United States Air Force today. The B-47 was the indispensable bridge between the propeller-driven past and the push-button future. A beautiful, deadly, and deeply flawed machine that held the line when the world was closest to the brink. The true measure of a weapon of mass destruction is not found in the cities it burns to ash, but in the wars it prevents by casting its long, terrifying shadow across the runway. The B-47 Stratojet won its war simply by existing. And then it faded into the desert, leaving behind a legacy written not in blood, but in the silence of a holocaust that never happened. Which factor do you believe was the most critical in forcing the rapid retirement of the B-47 Stratojet? A. The development of advanced Soviet surface-to-air missiles like the SA-2 guideline. B. The catastrophic structural fatigue caused by the shift to low-level bombing tactics. C. The introduction of intercontinental ballistic missiles and the longer-ranged B-52 Stratofortress. Let me know your choice and your reasoning in the comments below.